In graphs 27.1 and 27.2, we illustrated the efficiency condition for public goods provision. At an efficient level of public goods, it must be the case that the sum of the marginal benefits of public goods is equal to the marginal cost of providing the public good. We'll now consider what happens when public goods are provided privately, and we'll show that the efficiency condition will not be met, that too little public good is produced when private decisions lead to the overall public goods level. We'll assume that you and I are both privately shopping for fireworks, and that we'll display those fireworks in our backyards, each being able to enjoy the fireworks displayed by the other. On the vertical axis, we'll show the quantity of fireworks, Y1, that I will buy, and on the horizontal axis, we'll show the quantity of fireworks, Y2, that you'll buy. If I think that Y2 is 0, in other words, if I think that you don't buy any fireworks, I will buy fireworks until my marginal benefit from the fireworks is equal to the marginal cost of the fireworks I'm buying. The resulting quantity is indicated on the vertical axis as Y1, 0, my best response to you purchasing no fireworks at all. But if I think that you'll buy some positive quantity Y2, then I'll reduce the number of fireworks that I buy, because I already get to enjoy the ones you are buying. My best response to you buying fireworks then begins at Y1, 0, where I think you don't buy any fireworks, and decreases as you buy more fireworks, resulting in a best response function like the one drawn here. To find a Nash equilibrium to the game that we're implicitly playing as we shop for fireworks, we also have to know your best response function to any quantity of fireworks that I buy. We'll assume that you and I are identical, and so your best response function is the same as mine. If you think that I buy no fireworks, you'll buy fireworks until your marginal benefit is equal to the marginal cost of the fireworks, the quantity Y2, 0. But as I buy fireworks on the vertical axis, the number of fireworks you'll buy on the horizontal axis will decrease, because you already get to enjoy some of the fireworks that I'm buying. Since we're assuming that the two of us are identical, our best response functions must therefore cross along the 45-degree line. That intersection then gives us our Nash equilibrium strategies, because at that intersection we're both producing quantities that are best responses to the other. The overall quantity of fireworks that are being shot into the air in our backyards will then be equal to the sum of the fireworks that the two of us buy. Given the fireworks that you're buying, my best response is to buy fireworks until my marginal benefit is equal to the marginal cost of fireworks, which logically implies that the sum of our marginal benefits is greater than the marginal cost of fireworks at the equilibrium that we've identified. Efficiency requires that the sum of the marginal benefits is equal to the marginal cost, but in our Nash equilibrium, we're buying fireworks up to a point where the sum of the marginal benefits is greater than the marginal cost, which means that we're buying too few fireworks relative to the efficient quantity. The reason for this is that I don't consider the positive externality my fireworks have for you, and you don't consider the positive externalities your fireworks have for me. Notice that this problem already emerges when there are only two of us, and it only gets worse when there are more of us. The reason for that is that the positive externalities multiply as there are more of us, because every time I buy fireworks, I only consider my private benefit of those fireworks and not the positive externality that is imposed on lots of other people. The under-provision of public goods under private provision therefore is exacerbated as the number of people involved increases.